Good afternoon, and so today I'll be presenting our work on developing a model for GaN-based HEMTs. This work has been going on for quite a few years, and it has reached some stage. So I will basically discuss about the various features of this model and what is it capable right now. So the organization is we may have, I think it's not necessary, but some introductory slides. Then I will talk about our model, the charge control model, the drain current model, gate current model, the charge-based dynamic model, also the transient model, and I will also discuss about the compact model for FinHEMTs, which we have discussed, which is basically a variation of the model for HEMTs, and we talk about some of the validation, what we have done for this model. So why GaN? I think I had a lot of talks. So of course GaN has very interesting properties which make it suitable for high power, high frequency, high power because of its large band gap, large breakdown field strength, and high frequency. It has higher saturation velocity, and also the AlGaN system is attractive for HEMT devices, and it has, even when you compare it with AlGas gas, it has several advantages which make AlGaN GaN system very attractive for high power and high frequency applications. Of course, there are other systems which people are investigating now, like aluminum indium nitride on GaN and aluminum nitride on GaN systems for better performance. Just for the sake of, again, those who are not so familiar with HEMT, so it is very similar to a MOSFET. So many of the models which we discuss are derived from MOSFET models. There are some differences, of course. In the MOSFET, you have the gate and then the dielectric and then the substrate. Here, instead of the dielectric, you have a barrier layer, which is the AlGaN layer. But in the case of MOSFET, this oxide layer is very thin, maybe a nanometer of that order for present generation, whereas for HEMTs it can be quite thick. And of course, this has when you have a thick barrier layer, it will give lower gate capacitance and lower GM. In the case of a MOSFET, you have heavily doped source and drain. In this case, doping is not required, so it's a simpler process in that respect. In the case of MOSFET, you have a MOS gate, whereas in the case of HEMT, the basic structure has a Schottky gate, which has a problem because you have to deal with gate leakage. And because of that, you cannot go to forward gate voltages, and that limits the voltage swing. Of course, one can overcome that with mis-HEMTs. In the case of MOSFET, you have a heavily doped channel, whereas in this case, of course, you have an undoped channel. In the case of, that's why you get the high electron mobility. And of course, high mobility will lead to higher transconductance. Another major difference is the source drain overlap gate in the case of MOSFETs, whereas in this case it is underlap because you have what we call the access regions. Okay, the gate is separated from the source and drain, and this of course results in higher series resistance and also current collapse. You talk of the drain resistance, etc. So this is another difference. The other important difference is, in the case of a MOSFET, it is a normally off device usually, whereas in this case it is a normally on device. And this has a problem of, if it's a normally on device, you need dual power supply, complicated circuitry, drive circuitry, etc. But there is one more difference I would like to make, is that MOSFETs normally work in the inversion mode, where you are moving, when you turn on to off to on, you are inverting the channel, whereas HEMTs usually work in the accumulation mode. So you are actually going from depletion to accumulation to turn it on, and this has a advantage from a modeling perspective, because you don't have to deal with depletion charges. Normally in a MOSFET you have to consider the depletion bulk charge and then the inversion layer charge. Here, because you are working the accumulation mode, you don't have to deal with it. So that's why I put it in green actually. So these are some of the major differences. Otherwise these are quite similar devices. So many models are basically derived from the MOSFET models. And the other one major difference, I would say, is the traps, presence of traps in the gallium nitride. There are defects located across various regions of the device. Of course, the unintentionally doped buffer is usually N-type, but there are traps such as iron, magnesium, and there could be also defects. So there are traps all over the device, because mostly because the gallium nitride is grown on a foreign substrate, and one has to actually take care of them while modeling. So our basic model, of course, what we have, the charge-based model is based on, we have a core charge model, and then we have all the, and this core charge model is different from that in existing models. Of course, for example, talking of the Angelov model or ASM is of course a surface potential based model. So this is different. Even the MIT model, the virtual source model, is charge based, but it is different, and our model is different. The models the models are physical, and so these are all we are discussing. Of course, our model is a physical model similar to maybe ASM or MBS. And in our model, the state variables are what we call QNS and QND, which is the source electron density in 2deg and the drain electron density in 2deg, and based on all our equations are based on QNS and QND. So once we calculate QNS, we are able to calculate the QNS and QND. We are able to derive all the relations based on these two terms. So what we do is in our model, we actually calculate the 2deg charge considering the traps. So this is something different from some of the existing models. So what we do is we consider a trap level ET below the conduction band, and so these are the parameters. NT is the trap concentration, the trap activation energy ET, and of course D is the barrier layer thickness. So once we know this NT-ET, we have actually derived an analytical formulation. So what we assume is that all the traps below the Fermi level are occupied. So we consider a triangular potential well in the surface, and all the traps below the Fermi level are occupied, and then we can write down a series of very simple equations based on the electric field, which is charged by epsilon, and then we can actually calculate, and so this is what we are calculating. NTR is the actual the trap charge concentration, which is basically all the traps which are below the Fermi level. So this is basically integrating the Fermi function. So we can actually, with this, we are able to calculate analytically the trap concentration as a function of the gate voltage. So we not only calculate the 2deg concentration, so we can also calculate the trap concentration for any given voltage, and we can also calculate the trap concentration. NTRO is the trap concentration at threshold voltage, and so we can get a relation for the threshold voltage shift due to the presence of traps. And with this, we can get so this is actually we are validated with TCAD simulations that how the threshold voltage will shift with respect to the trap concentration. So this is for different trap concentration and also for different activation energy. So we have a scheme for actually calculating for any given gate voltage. We can calculate the 2-deck concentration considering the trap concentration, and so what we observe is so this is a very simple scheme. We have the same equations and we can get closed form expressions for both NS, which is the 2-deck concentration, and also the trap concentration. And so what we get is we can get the 2-deck density as we observe that the 2-deck density actually decreases as we increase the trap concentration. So, in fact, this was something which we observed that in analytic when you actually measure the mobility in the 2-deck, we get actual measurements, you get very high mobilities, more than 1,000 centimeters square per whole second. Whereas when you actually try to match using the models, you use very low values of mobility. The reason we feel is that because we are not considering the traps when we consider the 2-deck concentration. So actually you actually overestimate the 2-deck concentration, and in order to match the exact current values, you have to underestimate or you have to consider lower values of mobility. So the values of mobility which we are using in a compact model, are actually not the exact mobility values. So anyway, we are able to develop a model for the 2-deck concentrations based on the trap, and we use this model also for our transient modeling, where we can very easily model them because you also need the DC model to be perfect, the effect of traps in the DC model to be able to get you can actually reduce the number of parameters in the transient model. So anyway, so finally, so what we do is we use a charge linearization scheme, which is also there in BSIM. So it's a similar way to do it. So the electron charge in the channel is considered to be a linear variation from source to drain, and alpha m is the linearization parameter, and Vm is the charge at when this the voltage is is the average of the source and drain voltages, and then we do a linearization, and once we get this linearized form, so it is very easy to integrate, because you have to, in order to get the current, you have to do integrations, but this makes it very easy. So based on charge linearization, once you have this Qn is equal to in a linear form, you can take the drift diffusion equation and do a linearization, and you come up with expression for drain current in this form, which is in terms of QNS and QND, where QNS is the charge at the source end and QND is the charge at the drain end. So to consider the field dependent mobility, we again derived the equations and we come up with this form again in terms of QNS and QD is an effective drain voltage, which is given by this form, which is again a sort of expression. QDF can be when QND, so we calculate a QDS, which is in terms of which is the particular value of the drain charge when QND, the charge at the drain end, is greater than QDS, it is in the linear region. When it comes to QND is equal to QDS, is in the saturation region. So actually we can model the saturation effect. Also the current saturates when the drain charge goes to QDS, and we get both linear. So we get one expression, but it is a unified expression for both the linear and saturation regions. So this is the other interesting thing what we have in our model is the modeling of the access regions. Access region models is modeled in different ways. In many models it is considered as resistors, but in our model, which is similar to the MIT model, what we do is we consider them as transistors, and actually the access regions are ungated transistors in the sense, and so they behave, but it is if you actually take an ungated transistor, it will show saturation. So so when you put a transistor, it will show this type of behavior. So it's a nonlinear resistor in fact, and so all this transistor is exactly identical to the intrinsic transistor. All the parameters are the same, so you don't have additional parameters, but only the length is what it changes. And we have another one parameter, which is the threshold voltage of the access region transistor, which is varied to get the particular resistance. So an experimental, of course, we can show that it behaves like this. So basically what we have is the whole transistor is modeled as a series combination of 3 current sources. The center one is for the intrinsic transistor, and the other 2 are for the access region transistors. And of course, because they are in series, all the currents have to be same, and the voltages, internal node voltages, will have to adjust in order that all the currents are the same. And so this is the overall model of the DC model. And then we add on other effects such as DIBL, channel length modulation, vertical field dependence mobility, which is quite common with other models also, self-heating. So we have circuits to model the self-heating, and then we do all the Gummel symmetry test, cascode test, all the regular tests, and it goes through all the tests. And we have also done, because we have the access regions of different lengths. So source, drain, and source length, and the source access region on the source length side is different from the drain side, and we actually did the measurements by interchanging the source and drain of a transistor, and then we found that it matches. So the access region transistor model works. And then we did different validations, of course, for different devices from literature mostly, and for different gate lengths, and we could do the match for the DC part. So the DC part is sort of, we could validate, and we also in order to take care of the traps, we also did some, these are matches with TCAD with different trap concentrations on the considering different buffer trap concentration. These are all buffer trap concentration. Okay, so for different gate lengths. So also the derivatives of drain current. Then the gate current, that is another very important aspect of HEMT modeling. So we developed a model considering the different current mechanisms, that is Fowler-Nordheim, Poole-Frankel thermionic emission and defect assisted tunneling, and we derived expressions for the different current components, again in terms of QNS and QND, because then once we calculate the QNS and QND, we can very easily calculate all the different components. So just to give you an idea, so the IFN is the Fowler knot diameter current. All expressions you can see are in terms of QNS and QND, and this is already published. So so we have implemented the gate current model. The other important thing is when we the gate current model is not, it's not just sufficient to derive a model for gate current, but we have to see what part of the gate current flows to the source or what part flows to the drain, and only then we can actually implement it in a circuit simulation. So we actually derived the partitioning of gate current into gate to source and gate to drain components is essential for implementation. So and this is bias dependent. Okay, so it is not that so depending on the drain voltage and the source voltage, gate voltage, there will be different fractions going to the source and the drain. So so for each component we had to find a source component and drain component. And what we basically did, we sort of did a type of Watt-Dutton partitioning again in this case, and to see how much current flows to the source and the drain. The scheme is almost the same, and we can show here that the gate to drain current as a function of gate current, it actually is not a constant, but it actually changes with bias. So and we could sort of model that. And we did extensive validation with experimental data for different gate voltage, gate current characteristics. And also here we see the gate voltage variations for different drain to source voltage. So all these we did we could match our results with all this data. Okay, these are some more results. So we actually again modeled the different components of current. So different bias ranges, you have the different components of current will become important. So we could actually, because we have our total gate current is a summation of all the different components, we can see at which region which component becomes important. Then we developed the charge-based dynamic model. For that this is the total charges on the source and drain, and so again this is basically done using the Watt-Dutton partitioning scheme, and this is for the basically the same scheme as the Watt-Dutton partitioning scheme used in MOSFETs. And then we have this is the equivalent circuit for the intrinsic transistor, where we see the gate current. So we have the drain current, this is the DC current, we have the AC, that is basically the charge-based model. So we have the dynamic currents as a dq by dt, and we have the gate current here. This is the gate current, we have the source, gate to source component and the gate to drain component. And so these are all the basic equations. So this is the equivalent circuit model, and here of course we have the source and drain. Yeah, so we have the source and drain we have added, and this is the complete equivalent circuit considering the parasitics. Okay, and so actually we had to add one more element here, because in some experimental data we found that the transconductance, the DC transconductance is not matching with the what we may get from the AC from the S parameters. So so this is the overall complete equivalent circuit, including all the parasitics. Now coming to the transient. So what we observed is that we did some simulations, TCAT simulations, and we found that when we apply a pulse, okay, there are trapped electrons in the buffer, and because of these there is a negative potential is developed across in the buffer, and this leads to a change in threshold voltage. So that is how we have modeled it, and this negative potential we have through simulations, we have done extensive simulations, and we found how this varies with different trap parameters. And then what we did was we developed a model where the threshold voltage of the transistor is modulated, and basically if you have a pulse like this, we have a sub-circuit which actually consists of an RC. So one time constant is for the charging of the, you have one time constant, and the emission time constant is different. So that's why we have, so during the charging, this path will be operated. You have one time constant, and this is the discharge time. And so this voltage across the capacitor is put here, and then the threshold voltage is modified, and that by that we are able to actually model the transient effects. And we did a lot of simulation, and these are the results from the model. So we did a lot of TCAD simulations, and this is for the pulsed case, where we are able to, from the model, we are able to actually get the same behavior. And this is for pulsed measurements, where we see the actual current collapse. So this is for different pulse widths, 10 microseconds, 100 microseconds, 1 millisecond, and the model, through the model, we are able to actually match the characteristics. So this is, so this actually validates what we have been, achieving, trying to do. So again, there are some further transient model validation. This is actually the transient drain current characteristics from experiment. So we are able to match these results through our model. So this is some results we got from through Professor Nallatambi and for these devices, and we were able to, again, we tried to match with our model, and this is the DC part, model and experiment, output characteristics. So these are all 150 nanometer devices, and these are S parameters of the device, and this is a different gate to source and drain to, this is at VGS is minus 3 volt, VDS is 10 volt. So these are the match we got. So this is at a different gate voltage. Again, we got a good match, and this is for another gate voltage. So we got a very good match. So this is sort of the status. So we would like to do further validation, but at this point we are able to match a lot of our results. The extension of this work, we have also been developing a model for FinHEMTs. That is also a part of our activity. We are working on FinHEMTs. So we have been we have extended our model for planar HEMTs into FinHEMTs. So what happens in a FinHEMT is basically you have 3 gates wrapping around the channel, and this leads to a positive shift in threshold voltage, basically because you have the side gates which help to deplete the channel. So this gate will deplete the channel from both sides, and that leads to an increase in the threshold voltage. The current, again, there are 2 channels. One is the normal 2-deck channel, which is shown here, but you also have, this is actually MIS. So along you have an oxide on the fin, and then you have a gate metal, and so on the side it is like a MOSFET. So you have basically, when you increase the gate voltage, these 2 sides will get accumulated, and there will be an accumulation current flowing through the side walls, and so we have the total current will be the sum of the 2-deck current and the accumulation current. So this is modeled like that. So firstly, the threshold voltage model. So here you see that you have the side gates. So any charge, field lines originating from the charge at the interface can either end up in the gate, or it can end up on the side gate. So right, so the field lines are shown here. So the capacitance, you have capacitance due to the top gate, you have another capacitance to the side gate. Now the interesting thing is how you model the side gate, because it's like two plates which are like this. So it's not like parallel plate. So we do a sort of conformal mapping technique. Using that, we have developed expression for the capacitance, and this is published in this paper. So basically for wide fins, the side gate part can be neglected, but for narrow fins, C side for narrow fins, C side cannot be neglected. And so the C tri increases with reduction. You can see that when the fins, when the side gate capacitance is basically, when it becomes very narrow, the capacitance is mostly due to the side gate, whereas when it becomes very wide, it is mostly due to the tri gate. So we derived a relation for the threshold voltage of the tri gate, and here this it is given like this. So in this case, the capacitance, which is important, is that it is normally we put in the MOS relation, this Cox is farad per centimeter squared, but in this case we cannot put farad per centimeter squared. It has to be farad per centimeter because it's per length, and so the relation is like this. So this is somewhat different from the expression for threshold voltage of HEMT, and with just this small modification, we are able to actually match the threshold voltage of FIN-HEMTs. So basically, if you consider the planar HEMT model and the FIN-HEMT model, there are very few changes. The gate capacitance in the planar HEMT is given by Cg, whereas in this case it is the tri-gate capacitance. Normally in planar HEMT it is farad per centimeter squared, here it is farad per centimeter. The two-deck density also, in this case in the HEMT, instead of the two-deck density in planar HEMT we express in terms of coulomb per centimeter squared, here we have to express in terms of coulomb per centimeter. Okay, it's per unit length, because right. And what we do is we do a simple transformation, NST instead of NS, we C tri by Cg into NS. So whatever you have for the planar HEMT, you can just do a simple transformation and you get it. So, and the electron charge, Y can be at the source end or drain end, we can get this will be Q and Y will also be coulomb per centimeter. Q and Y will be coulomb per centimeter, NST is per centimeter. Okay. And of course, your thermal resistance in a FIN-HEMT is different, because you have the fins, and then you have if you have a fin, you have the gate metal going like this. So the gate metal actually takes off some heat. Okay, so the thermal resistance are going to be different, and so this we have been able to model this way. And this is the expression for drain current which I showed. So here it is proportional to the width. So instead of that, now in this case, this QNS and QND are, because it's coulomb per centimeter, and here it was coulomb per centimeter squared. So you don't have width there. It is only as a function of length. And of course, alpha m here it is, I think here it is coulomb per coulomb per centimeter squared per centimeter. So, and that will be coulomb per centimeter per centimeter. So that is, because of that you get the same units actually. And then we also developed an expression for the accumulation current which flows along the side walls, and you get the total current. So we have validated all this with experimental data available in literature, and we can see that for different fin widths, our model, our drain current model is able to match with experimental data available in literature, and we can also see the threshold voltage shift. You can see the change in gate voltage, how the drain current changes. So this gives a very good match. In the case of fin HEMTs, the access regions can be made in different ways, we have seen. So here in this first case on the left, it is a complete fin all the way from the source to the drain head. In the second case, actually the fin portion is only under the gate. So this has an advantage because your access region resistances will be less, because the width of the access region is more than the fin, and so you can actually achieve much lower access region lengths. And here in the third case, you can see that it is partially fin, the access region, partially a fin type, partially a planar type. So what we have done is, because we model the access regions as transistors in our model, we can have this access region model the same as fin model or a planar HEMT model. And with that, we are able to, we have found data in literature for all these types of devices, and we are able to match with all these, we got very good match with all these data. And in fact, this has been published very recently in this year, 2023. All these match with the experiments in IEEE transactions. So summary, we have model, of course, implemented in Verilog A, calculates QNS and QND for the given bias from the charge control model, use QNS and QND to calculate drain current, gate to source, all these. Physical based model, small parameter set, because most of it is physical, the parameter set is small, and so it is easy to extract. So the advantage of a physical model is that because we have smaller parameter set, it is easier to extract. I think I'd just like to, maybe we'll discuss, okay. I just contradicting what Dr. Leclerc said in the morning. So, okay. So some special features are the 2-deg and trapped electron densities are calculated simultaneously. There's a physical bias dependent gate current partitioning model is used. The planar HEMT model can easily be extended for fin HEMTs. And for model validation, extensive validation of experimental data has been done. Of course, we can do more, and accurately captures DC, RF, and transient characteristics as far as we can see. And thank you. And before I end, I have to acknowledge my colleagues who have been involved in this work, as well as a lot of our students. It started with Naveen's PhD thesis, and all these people have worked, and Vigneshwar is also here, Shujan, Ramdas, Shruti, Ajay, so all of them. In fact, Ajay is presently in France, so all of them have contributed to this work over a long period of time. Thank you.
Thank you very much. Now the paper is open for question. Yes?
So I just wanted to get an idea why, since access regions are ungated regions, right? Why have you used in your model source connected transistors?
Yeah. Because it mimics the resistance effect, basically, actually, if there can be velocity saturation in the access regions also, correct? And so it is not going to be a linear resistance. So it could mimic the behavior of the access regions as a non-linear resistance, basically.
Ungated regions, let's say, if I directly connect it to ground,
Yes.
it will behave as a non-linear resistor. So I don't know. I'm not able to get it. Why I have to connect it with the source?
No, I'm not connected to source. Only the first, the source side is connected to source. Drain side is not connected to
That
source.
is connected. That is connected to a drain of intrinsic transistor.
Yes, so
That
it is to that node, you know. So current is flowing, so it is flowing in this direction. So basically, each one will act as a nonlinear resistor. So it is to that internal node it is connected. That is between the drain of the intrinsic transistor and the source of the axis signal transistor.
So okay, for example, from the circuit designer point of view, would a circuit designer prefer a simple nonlinear resistor or three?
No,
transistors
because
in
these
series?
are internal nodes. The circuit designer will not see all
Still,
this.
it will increase the simulation time, right? Because there are further more nodes in the Verilog, let's say.
Yeah, I mean, you can say that, but it is these are internal nodes basically for just for simulation.
Okay, one more thing. The model uses trap concentration initially while deriving, right? Those are assumed as interface traps. And so
These are all buffer traps. We have considered only buffer traps.
So, but there is an assumption that these are a sheet of charge. There is no
There is not a sheet of charge. We have considered for this case we have considered uniform buffer charges, buffer trap distribution. But
Yes.
The scheme we have used, we can actually consider any type of charge distribution because it's analytical. If you can consider a sheet of charge and all that, so the equations may change.
So first thing, initially in the model, already the trap concentration is used to obtain a threshold voltage shift. Then again during the transit.
No, we are not considering. So basically, the threshold voltage shift due to the traps will come about because of the NS variation. You know, the
yeah, that is already incorporated.
Yeah. If the trap concentration increases, the threshold voltage shift will be more. So that is now inbuilt into the model.
Okay. So finally, then again, the model uses RC networks. That is due to the trapping only.
Yeah, that is due to the dynamic.
Yeah.
So this is basically what I am saying is for the DC part. So the DC part itself, we are calculating the effect of traps. So even in dynamic model, you need a DC part, the effect of traps. So it actually reduces. We have seen compared to other models, it actually reduces the number of parameters we need to model the effect of traps for the dynamic simulations.
Okay. Fine.
One time for one question.
Yeah.
How is the convergence with the gate current?
We don't have convergence issues. We have not seen any convergence issues. Really?
If you have few transistors,
Maybe we have not tested that. Maybe we have to see that.
I have a question. How many parameters in your model, and do you have a process flow to extract?
Yeah,
all
yeah.
these
We have a process flow. We do have. So the parameter set is quite small. I cannot give you the exact number, but I mean, because it's very physical. So once you make it more physical, the parameter set will become small. So you can. It makes it easier to extract also.
Okay. Thank you again.
Thank you. Thank you. Thank you.
So,
Long live India and France friendship.